In this video, we're going to talk about monotonic sequences, bounded sequences, what it means for a sequence to be bounded above and bounded below. And then we're going to use these concepts and definitions to discuss the bounded monotonic sequence theorem. Then we're going to look at a few examples of sequences and try to determine whether they're monotonic or not, or bounded or not. Then we're also going to use the bounded monotonic sequence theorem to show that a particular sequence converges. So let's talk about what monotonic means. We say that a sequence is monotonic if the following is true. If the sequence is non-decreasing and this is for all n, or if the sequence is non-increasing for all n. And you might be thinking to yourself, why use the word non-decreasing? Why not just say increasing? Or why use the word non-increasing? Why not just say decreasing? This non-decreasing leaves us the ability to have a bunch of sequence terms that are exactly the same. So it's going to turn our less than signs into less than or equal to signs, or greater than signs into greater than or equal to signs. So let's just focus on this non-decreasing case. If it's non-decreasing, that means a sub n and a sub n plus 1 always satisfy this inequality for all n. If it's not decreasing, a sub n plus 1 has to be greater than or possibly equal to a sub n for all n. And remember how a sub n plus 1 and a sub n are related to each other. This is just one term, and that's the one after it. So what this is saying is my two consecutive terms can sometimes be equal, or the one after has to be greater than the one before. And so a sequence that's non-decreasing for all n is monotonic. Here are a couple of examples. This one's actually strictly increasing. A sub n plus 1 is always greater than a sub n in this picture, but this is definitely monotonic. Here's another example of monotonic. You might be in the case where you've got a bunch of points that look like this, and they seem to be getting closer and closer to some value. And maybe that value is y equals L, just for example. So that's non-decreasing. It's almost like increasing, but it allows us to say this one's always greater than this one, except sometimes when they're equal to each other. Okay. Another possibility for a monotonic sequence is it's non-increasing, which means it's usually decreasing, or occasionally the terms of the sequence are equal to each other. So now when I compare a sub n to the next term, a sub n plus 1, these guys are going to be less than or equal to the terms before. Now these guys were all increasing, or non-decreasing to be more specific, more precise. It's possible that we could have a non-increasing sequence that's monotonic that would look like this. Maybe it has this behavior. See, as I go from term to term, this y value is smaller than that y value, and this one is smaller than that one, and this one is smaller than that one, and so on. And so these guys are all getting smaller and smaller, and they're never increasing. There's never one y value over here. There's never an n plus 1th term that is higher than the one before it. When I say higher, I mean that distance from the x-axis is not larger for the one after it. So this one is decreasing. Another possibility for a non-increasing sequence might be something that looks like this. So that's clearly decreasing. Or we might have something that looks almost like a parabola. Also decreasing. Okay, so all of those are monotonic. Now here's an example of one that's not monotonic. Because I go from term to term, I'm decreasing, and then I go from here to here, I'm increasing, and then decreasing, and then increasing, and then decreasing, and then increasing. So this one's not monotonic, because sometimes it's increasing and sometimes it's decreasing, but it's never non-decreasing for its entire domain or all n values, or non-increasing for all n values. This is sometimes increasing, or sometimes decreasing and sometimes increasing. So this is not monotonic in this picture. But the others are all monotonic. That one's non-decreasing, that one's non-decreasing. This one's non-increasing, that one's non-increasing, and this one's non-increasing. So all of those are monotonic sequences. Now let's talk about what it means for a sequence to be bounded. So let's start with bounded below. We say that a sequence is bounded below if the following is true. If the a sub n are always greater than or equal to some number m. That's bounded below. Now graphically what that means is this represents a line. That represents y equals m. It's a horizontal line. And this just means the a sub n values, those points on our graph for a sub n, they're all going to lie above this line y equals m. So maybe they're here, and here, and here, and here, here, here. I mean, it could be doing anything. Go up here, and so on. So this might be what our graph looks like when it's bounded below. The entire graph of a sub n lies above the line y equals m. We say a sequence is bounded above if the following is true. A sub n is always less than or equal to n for some n. And this is for all integers n, or all n in the domain of a sub n. And this is for all lowercase n in the domain of a sub n as well. So we say a sequence is bounded above if the entire sequence lies below a line given by y equals n. So y equals n might be up here. And maybe our sequence looks like this. Maybe it gets really close to y equals n. All right. Oops, not y. That's a sub n, and that's n. And that's n, and that's a sub n. But on the y-axis and the x-axis like we're used to. Okay, so now we say a sequence is bounded in general. Not just bounded below or bounded above, but we say it's bounded if the sequence is bounded below and bounded above. All right, and specifically what that would mean is a sub n lies between two lines given by y equals m and y equals n. For all n, and of course that's for some specific m and n. So y equals m might be down here. Y equals n might be up here. And a bounded sequence just lies in between these two lines. So maybe it looks like this. Who knows? Or here's y equals n and y equals m. It might look like this. Okay, so these are all bounded. Now let's look back at our monotonic sequences and see which ones of those are bounded. Okay, so now I'm here. Is this bounded? Bounded above or bounded below? Well, notice that the y's just keep increasing, so it's definitely bounded above or bounded below. So let's say y equals m is down here. All of those points are above that line. But is there any line that they're all below? Well, I don't think so. Look, it seems to be linear and it's going to infinity. So this one's bounded above, or excuse me, I'm saying the wrong thing. Bounded below. It's bounded below the whole time. And it's monotonic, and it just goes on to infinity, so it's not bounded above. Now this one is clearly bounded above because of that line y equals l that I drew in the picture. Is it also bounded below? I hope you said yes, because look at all those points. I can draw them all above this line, y equals m. So this graph, the graph of a sub n, lies between y equals m and y equals l. So it's bounded. It's bounded above and below. If it's both, it's just bounded. What about this one? Is it bounded above, below, or both? This one's both. It's bounded above by this line. I'll put an n there. Bounded below by this line. So that one's bounded. What about this one? Well, it's decreasing the whole time, right? If it's decreasing, it definitely lies below this line, y equals m or n. It really doesn't matter what the letter is. It represents a number, right? So the sequence lies entirely below this line, so it's bounded above. But it's not bounded below because it just keeps decreasing. If I were able to draw all the points, it would just keep going. Anytime I draw a line, there's going to be a point on the other side of the line. And the same thing is true here. This one's bounded above, but not below. And it's decreasing. Now this one was the one graph that we did that was not monotonic, but notice it's bounded. It looks like a sub n equals -1 to the n plus 1, because it starts positive, negative, positive, negative, positive, negative. It's not monotonic, but it is bounded. Okay. So those are that's what those terms mean. Monotonic means non-decreasing the whole time. Just basically increasing with possibility of sometimes being equal. Or non-increasing the whole time. Usually decreasing, but with the possibility of sometimes having equal terms from term to term. That's monotonic. It has one behavior over the long term, the long haul. It's dependable. You know exactly what's going to happen to this. This just keeps going up. This just keeps going up. This just keeps going down, and this one just keeps going down. or maybe they stay constant for a while. They stay constant for a while and then they go down. Not monotonic means sometimes they go down, sometimes they go up, sometimes they go down, sometimes they go up. Maybe it goes down for a while, but then it comes back. So that's not monotonic. Now we talk about sequences being bounded. If it's we say it's bounded below if the sequence lies above a line, y equals some constant. We say a sequence is bounded above if the entire sequence lies below some line. And we say it's bounded if it lies in between two horizontal lines. The entire graph does. Now let's put all these pieces together in what's called the bounded monotonic sequence theorem. Here's the theorem. It says, and I'm using THM as an abbreviation for theorem, every bounded monotonic sequence converges. And that's it. And what's nice about this is if you can prove that a sequence is bounded and monotonic, you know it converges. Now, that does not tell you what it converges to. We have no idea what the limit might be. We'd have to find that out through other means. But I know I can prove that if a sequence is bounded and it's monotonic, this theorem tells me we're guaranteed it converges to something. I might not know what it is, but it converges to something. Okay, so let's do an example with this. Let's say you have a sub n equals 2 over n. Very simple example. Question is it bounded and is it monotonic? Well, first of all, let's talk about whether or not it's bounded. It might help just to get some intuitive sense of what's going on if we start listing a sub 1, a sub 2, a sub 3, a sub 4, and so on, just to get a sense of what's happening, at least at the beginning of our sequence. When n equals 1, I've got 2 divided by 1, that's 2. When n equals 2, I've got 2 over 2, which is 1. When n equals 3, we've got 2/3, which we know is about 0.67. Now, when n equals 4, we get 1/2. When n equals 5, we get 2 over 5, that's 0.4. When n equals 6, we get 2 over 6, that's 1/3, and you just keep going. And that's our sequence. It might be even easier to see if I use decimal approximations. So that's a 2, that's a 1, that's a 0.67. This is a 0.5, that's a 0.4, that's a 0.33, and so on. So notice I've got a 2, a 1, a fraction, a smaller fraction, a smaller fraction, a smaller fraction. And this is actually one where we wouldn't need this sequence, the bounded monotonic sequence theorem. We know this one converges to 0 because as n goes to infinity, 2 over a large number is going to be a very small positive number. We're going to get 0. So we know this converges to 0, but I just wanted to show you one where we could show that it's clearly bounded and monotonic. So let's talk about bounded. Is it bounded? Let's just draw it. When n equals 1, we get 2. When n equals 2, we get 1. When n equals 3, we get 2/3. When n equals 4, we get 1/2. When n equals 5, we get 0.4. When n equals 6, we get 0.33, and so on. I think it is bounded. It all definitely lies below the line y equals, let's say, 2.1. This is never going to be greater than 2. Because as n increases, that fraction is going to decrease. Now, since n is always positive, I'm never going to get 0 out of this. There's no n value that I could plug in where I'd get 2 over something is going to give me a 0. So this is also bounded below by the x-axis, by y equals 0. So we could say, yes, this is bounded. Because a sub n lies between 0 and 2.1. And is it monotonic? Well, I think it is. We can see that they're getting smaller and smaller. Now we might want to prove that it's monotonic by looking at a sub n plus 1 and a sub n. So here's a sub n, and I want to compare that to a sub n plus 1. Now the numerators are the same. The numerators are just a 2. In this one I'm dividing 2 into n pieces, and with this one I'm dividing 2 into n plus 1 pieces. So I'm dividing it into more pieces. Denominator is larger, so that our fraction is smaller. So a sub n plus 1 is strictly less than a sub n for all n. And if that's true, a sub n is always less than a sub n plus 1, or excuse me, greater than a sub n plus 1, then this is monotonic. So a sub n is bounded, a sub n is monotonic. So by the bounded monotonic sequence theorem, a sub n converges. Now this is one where we already knew the answer. We know it converges to 0 because we can take the limit as n goes to infinity. But we're just doing that as an illustration. Let's look at another one. Let's say our sequence is b sub n, which is 1 plus negative 1 to the n. Well, b sub 1 is 1 plus negative 1 to the first. So that's 1 minus 1, which is 0. B sub 2 is 1 plus negative 1 squared. 1 plus 1 is 2. B sub 3 is 1 plus negative 1 cubed. So that's 1 plus negative 1, which is 0. Well, isn't this just going to alternate between negative 1 and 1? When that exponent, which is the same as that subscript, whenever that exponent is odd, I'm going to get a negative 1. And I'll have 1 plus negative 1, and that'll give me a 0. And whenever that exponent is even, negative 1 to an even power is a positive 1. And 1 plus 1 is 2. And so we get 0, 2, 0, 2, 0, 2, and it goes on and on. Now we know already that since this has two subsequences that converge to different numbers, half the time it converges to 0, the other half of the time it converges to 2. So my graph looks like this. At n equals 1, we get 0. At n equals 2, we get 2. Then we get 0. Then we get 2. Then we get 0. Then we get 2. Then we get 0. And so on. That's a 1, 2, 3, 4, 5, 6, 7, and so on. Okay, so we know that that's true. We know that this diverges from what we've already talked about subsequences. But let's look at the bounded monotonic sequence theorem. Is it monotonic? I hope you said no, because it increases, then it decreases, then it increases, then it decreases, it increases. So it's not monotonic. So that theorem, the bounded monotonic sequence theorem, does not apply. But I might want to know, is it bounded? Does it lie in between two lines? Oh, sure. I can draw two lines. Here's y equals 2.1, and y equals, say, negative 0.1. 0 and 2 definitely lie in between those two lines. So we can say, just from this example, that b sub n is bounded, but it's not monotonic. And that means the bounded monotonic sequence theorem does not apply. So that theorem is not going to tell us anything about this sequence. We've got to do something else. We would use the fact that we've got two subsequences that converge to different values to show that this limit, or the limit of b sub n, does not exist. So that sequence diverges. Okay, let me show you one that we could not solve any other way. We can't solve it without the bounded monotonic sequence theorem. This is kind of a fun problem. It's from the textbook. So we've got a sequence. It's got a square root of 2 as its first term, a square root of 2 plus the square root of 2 as its second term, and then 2 plus 2, or 2 plus the square root of 2 plus the square root of 2 as its third term, and so on. So that's our sequence. So the first thing it asks us to do is to write a recursion formula for a sub n for n greater than or equal to 2. Well, the way recursion formulas work, usually you have to have somewhere to start. So someone's going to give you a sub 1 is square root of 2. And then we're going to say, okay, how do we get from a sub 1 to a sub 2? You notice that a sub 1 is right here. So I think a sub 2, that's that whole thing, is square root of 2 plus a sub 1. Because if I replace that a sub 1 at the square root of 2, I get a sub 2, so that works. Let's see if the same is true for a sub 3. A sub 3 is right here. Can I use this same formula? A sub 3 is the square root of 2 plus a sub 2. Does that work? Well, there's a sub 2. Yeah, I think that is the square root of 2 plus a sub 2. So I think this continues to hold, provided that this pattern continues past the dots. We're just assuming that that's true. In general, it looks like a sub n plus 1 is the square root of 2 plus the last term. If this is a sub n plus 1, that's going to be an a sub n. So that's my formula. And it's true for n greater than or equal to, it says 2, but I'm just going to write for n greater than or equal to 1, it's true. I guess I could write this as a sub n, and that is a sub n minus 1 if I wanted it to start at 2. But I'm just going to do this instead. Okay. Alright, so they wanted us to write a recursion formula for a sub n, and we did. I think I'm gonna back out of what I just said. They want a sub n, not a sub n plus 1. So I'm going to call this a sub n. And then instead of a sub n here, this index has to be 1 less than this one, so I'll call this a sub n minus 1. And this will be true for n greater than or equal to 2. So when n is 2, I'll get a sub 1, and this will be a sub 2, which is that first one. So we'll do this one instead. They're equivalent, but this is actually what the textbook asked us for. So let's make sure we answer the question that they asked us for. Or they answer the question that they asked us, excuse me. Alright, so now we want to use the bounded monotonic sequence theorem to show that this sequence converges. Well, that implies that it must be bounded and it must be monotonic. So let's think about how it must be bounded. Is it bounded? It is bounded, and how do we know? Well, let's think about it. A sub 1 is square root of 2. A sub 2 takes A sub 1, which is a number, it adds something to it, and then it takes its square root. That has to be, I believe that has to be greater than square root of 2, doesn't it? Yes, it does have to be greater than square root of 2. Because if A sub 1 was 0, I'd just get square root of 2 and square root of 2. Now under the radical, I've got square root of 2 plus something extra, and that something is positive. So this is larger than this, and this is larger than this. So in general, I said bounded. It's also bounded. But what I'm proving right now is that it's monotonic. A sub n is monotonic because I can say square root of 2 is strictly less than square root of 2 plus square root of 2, which is strictly less than square root of 2 plus root 2 plus root 2, like that. And this is always true. So in general, A sub n is going to be less than A sub n plus 1. Because A sub n plus 1, remember from our formula up here, that is the square root of 2 plus A sub n. So if this is true for all n, well then the sequence is monotonic. Okay, now I also want to show that it's bounded. Well, if it's behaving like this one's always greater than the last one. At n equals 1, we get square root of 2. At n equals 2, we get square root of 2 plus root 2. I don't know what that is off the top of my head, so I'm just going to use my calculator for that. That's about 1.85. And square root of 2 is about 1.4. And then to get A sub 3, I'm going to add 2 to that and then take the square root. And so I get about 1.96. Now I just showed that it was monotonic. Question is it bounded above? Looks like it just keeps increasing, doesn't it? It's increasing and increasing and increasing. I don't know that there's any guarantee that it's bounded above. So I don't know that that can be proven. Oh well, okay. So we can see from this graph, we can see that it's all definitely greater than square root of 2. So we could just do square root of 2 minus 1 as our lower bound. So it's definitely bounded below. But I'm not sure about bounded above. That might work. It might not. If the limit exists, it's definitely bounded above, because it would be approaching that limit. But it might just increase and increase and increase forever. Okay. Let's think about that a little bit more. Now, so I was able to prove it's monotonic, and I was able to prove it's bounded below, but I'm not 100% sure about the bounded above. So let's try to find the limit, if we can. And I think this is pretty cool. Since we have this inequality down here, or excuse me, this equation here that describes the relationship between a sub n and a sub n minus 1, we can actually take the limit of both sides using our limit laws, using our theorems, and provided that the limit exists, we can find the value of the limit. So that's what we're going to do. To find this limit, we're going to start by assuming that the limit exists. So we're going to assume L is finite and assume it exists. Then the limit as n goes to infinity of a sub n is equal to the limit as n goes to infinity of the square root of 2 plus a sub n minus 1. Because those are the same thing. Now, here is the key. If I've got a sequence and it looks like this, maybe they're approaching some value, and I'm taking the limit as of a sub n as n goes to infinity, I'm saying to myself, well, what happens to the values of a sub n on this graph? What are they approaching? And then I'm saying to myself, well, what happens to the values of a sub n minus 1? Well, those are just the terms before it. If a sub n is going to 3, a sub n minus 1, it's going to 3 as well. They're just going like one step later, like they're just behind you. But they're still moving toward 3. Say it's not a race. We're all getting to 3 eventually. So yeah, this limit and this limit are going to be the same. The limit of a sub n minus 1 and the limit of a sub n are exactly the same. So we're assuming that this limit exists and it's called L. So we'll have L on this side equals the limit as n goes to infinity of this. The square root of 2 plus a sub n minus 1. Now because of limit laws, I can pull the limit inside here. And then the limit of 2 is just 2. And then the limit of a sub n minus 1, well, that's just going to be L as well. Because if this guy is going to L, this guy is going to L as well. It's just one step behind. So we've got L equals the square root of 2 plus L. And from this inequality we see L has to be a positive square root. So L is equal to this positive square root. So L is greater than or equal to 0. Okay, with that in mind, I'm trying to get L by itself, so I'll solve this equation for L by squaring both sides. So we've got L squared equals 2 plus L, because the square root and the squaring function undo each other. Then we'll subtract the L from both sides, and we'll subtract the 2 from both sides, and we get this. Now this factors. I need two numbers that multiply to give me 2 that add to negative 1. Or excuse me, multiply to give me negative 2 that add to negative 1. 2 and 1 will work if they have opposite signs. If the 2 is negative and the 1 is positive, I think that's going to be enough. Negative 2 times L is negative 2. L times 1 is 1. So negative 2L plus 1 is negative 1L. That's my middle term. So this times this is 0, which means that L equals 2 or L equals negative 1. But we said earlier, L is this positive square root, so it can't be the negative 1. We also see from our graph, it's never going to be approaching negative 1. Apparently it's approaching 2. So if the limit exists, and apparently it does, these values are getting closer and closer to 2. And if they're getting closer to 2 and they're monotonic, they're definitely bounded above by like y equals 2.1. Let's see. Okay, so we were asked to find that limit, and my work is a little messy this time. And I've got this integration by parts stuff down here. Guys, sorry, I'm just trying to save a tree. We've got the limit as n goes to infinity of a sub n is equal to 2. And the way we did that was we took the limit of this equation, this one right here. We took the limit of both sides as n goes to infinity and used the fact that the limit of a sub n is L when the limit of a sub n minus 1 is L. And then we just solved that equation for L. And so that is the bounded monotonic sequence theorem. The theorem says that every bounded monotonic sequence converges. So even if you don't know what it converges to, if you can prove that a sequence is monotonic, so it's a non-decreasing for all n or a non-increasing for all n, and it's bounded, so it's in between two horizontal lines, in between two numbers, y equals m and y equals n. then we're guaranteed it converges. Now, again, remember what monotonic means. Monotonic just means non-decreasing, which basically means increasing, but they could possibly be equal to each other. Or non-increasing, which basically means decreasing, but some of the points could be equal to each other, some of the y values on this graph. If it's increasing sometimes, decreasing sometimes, it's not monotonic. Now, bounded above and bounded below just mean the graph is entirely above a line, and that means it's bounded below, or it's entirely below some line. That means it's bounded above. And if it's both bounded above and bounded below, we say that this sequence is bounded. Now, if the sequence is bounded, but it's not monotonic, there's no guarantees that it converges. And if the sequence is monotonic, but it's not bounded, there's no guarantee that it converges. But when we put those two pieces together, when we have a sequence that is both bounded above and below, and it's monotonic, those values have to approach something. So it's stuck in between these two lines. If it's going up, it's got to approach a value that's below y equals L here. If it's going down, it has to approach a value that's above y equals m here. Now, if it's monotonic and it's not bounded, proves nothing. If it's not monotonic and it's bounded, it proves nothing. But if you have the fact that it's bounded, like this picture, it's in between the two lines and it's increasing, or it's in between the two lines and it's decreasing. It's stuck, it can't go beyond those two lines. If it's decreasing, it's got to converge to something. If it's increasing, it's got to converge to something. And that's what the bounded monotonic sequence theorem says.